Hello friends, today's question. Two blocks of masses 2 kg and capital M are at rest on an inclined plane and are separated by a distance of 6 meters as shown. The coefficient of friction between each block and the inclined plane is 0.25. The 2 kg block is given a velocity of 10 meters per second up the inclined plane. It collides with mass M, comes back and has a velocity of 1 meter per second when it reaches its initial position. The other block M after collision moves 0.5 meter up and comes to rest. Calculate the coefficient of restitution between the blocks and the mass of block M. So it is given sin theta and tan theta are approximately equal to 0.05 and G is to be taken as 10. So these are the two blocks 2 kg and capital M. Initial distance between them is 6 meter and angle of inclination of the inclined plane is given as theta. So let us suppose this we can say 2 kg is represented by small m. So in this case we are supposed to find out two things. First is the coefficient of restitution and another one is the mass of the block capital M. So first of all, let's find out the coefficient of restitution. And by the definition or the formula for coefficient of restitution, it is basically, you can say, the relative speed of the blocks before collision, after collision rather, and then it will be divided by relative speed of the before collision. Okay. So it means we have to find out the velocity of M and capital M after collision as well as before collision, and then from there we can find out its coefficient of restitution. Okay. So first of all, let's find out part A and discuss for before collision. So before collision, it is given that our mass M angle theta, and this is our mass M. Let us suppose its initial position is represented as A, and the position at which it is going to make a collision with capital M is represented by B. Okay. So this distance is our 6 meter. At this position, it will collide with capital M. So let us say that A is the initial position of mass M, and B is the final position of mass M at which it collides with mass capital M. So you can say that this is mass small m. It is moving up the inclined plane with the acceleration of a1, and we have mg vertical downward. This can be divided into two components. This will have theta, So mg cos of theta, and this will be mg sine of theta. As it is moving up the inclined plane, so there will be a friction Fr down the inclined plane, and we are going to have a normal, let us suppose n, this way, and this is position number A. You can say for mass m, which is 2 kg, A1 is the acceleration up the inclined plane. If A1 is the acceleration up the inclined plane, therefore we can write the equation as m times A1 will be equal to mg sine of theta plus Fr, and we can calculate Fr. Fr will be equal to mu into n. N is equal to mg cos theta, so we can say our Fr is equal to mu mg cos of theta. So we substitute the value of Fr, we get m. A1 is equal to mg sine of theta plus mu mg cos of theta. M gets cancels throughout, so we get acceleration A1 is equal to g sine of theta plus mu cos of theta, and we are given the value of sine theta as 0.05 and g is 10. Therefore we can find out that our acceleration A1 is equal to 10.05 plus mu is given as 0.25 multiplied by cos of theta, which will be coming approximately 0.99. So we can say A1 is equal to 2.9. But because of the friction, this acceleration will be nothing but the deceleration. So this is the retardation for mass capital M, small m. Therefore we can say A1 is equal to minus of 2.9 meter per second square. Now we also assume that this is our mass m. It starts from position A, and the capital M is at position B, and we say that the final velocity of mass m at position B is given as, this is 6 meter, is v1. Okay, so it means final velocity of mass m at B just before collision is suppose v1, and initial velocity is already given to us, that is 10 meter per second. Initial velocity of mass m at A is given as u1, which is equal to 10, and we already said that its acceleration or retardation is given as A. retardation mass m is given as A1, which is minus 2.9, which we already calculated. So we can find out the final velocity just before collision, that is V1. So we can use the equation, using the equation of kinematics, V square minus U square is equal to 2as, and here s is nothing but this 6 meter. We substitute the value, we get V1 square minus U is our 10, and this is minus 2 into 2.9 multiplied by 6. So we can say our V1 square is equal to 100 minus 12 into 2.9, and you can find out this V1 will be coming approximately equal to 8.8 rather. So we can say V is equal to 100 minus 35.7 square root, or we can say V1 is equal to approximately 8 meter per second. So this is the velocity of mass m just before collision at point B. This is the velocity of mass m at point B just before collision. Now let's find out, consider the case for after collision. Now for after collision, it is said that this is initial position, and here it is going to collide with capital M. So this is our final position of mass m. After collision, it is going to move in the downward direction. Let us suppose the acceleration is given as A2, and it is going to come back to its initial position, that is A position. So the distance between the two will still be 6. So after collision, you can say mass m return to its initial position A with a velocity let us suppose that is given as v2 prime, and with the acceleration A2, with acceleration A2. In this case also, once again, the distance will be 6 meter. So therefore, we can further, this is point B, mass m, and we are going to have mg in the downward direction. This is theta. So in two components, this will be also theta. So we have mg cos of theta, and this will be mg sine of theta. Now the friction will be acting up the inclined plane Fr, and we have a normal n, and acceleration is A2. Therefore, we can write once again the equation for can see acceleration. You can say ma2 is equal to mg sine of theta minus fr, and fr we know is mu normal, or we can say mu mg cos of theta. We substitute here, we get ma2 is equal to mg sine theta minus mu mg cos of theta. M cancels out throughout, therefore we get the acceleration a2 rather is equal to g sine of theta minus mu cos of theta. Substituting value, we get a2, g is 10, sine theta is given as 0.05, minus mu is 0.25, 0.99. So therefore you get a2 is equal to minus 1.9 meter per second square. So once again, this is our retardation. Okay. Now we said that the velocity of small m at point B is v2 prime. So we said that velocity of mass m down the plane is v2 prime, which is after the collision, or we can say at point B. Next, it is also given that the final velocity of mass m at point A after collision is given as 1 meter per second square. So you can see final velocity of mass m at A after collision is given as, let us suppose, is u2, and it is given as 1. And acceleration we already know is a2, and the distance is once again 6. So we can use the equation of kinematics and find out our v2 prime. Using equation of kinematics, v square minus u square is equal to 2as. So v is our final velocity, that is given as 1. So here u2 is equal to v, and u is equal to u2 prime, and a is our a2, which is minus 1.9, and s is 6. This is given as 1. So 1 minus v2 prime is equal to 2 minus a is 1.9 and s is given as 6. So from here we can say that our v2 prime is equal to 1 plus, this will be coming as 2 into 1.9 into 6, which is equal to 24.1. So therefore we can say v2 prime is approximately equal to 5 meter per second. So So this is the velocity of mass m after the collision, okay, down the inclined plane. This is the velocity of mass m immediately after the collision. After the collision. Now we are going to concentrate for now mass capital M. So initially the mass capital M was at rest. Initially means before collision. So you can say for mass capital M, before collision, mass capital M was at rest. Now we are going to consider after collision. You can say after collision, for mass capital M. Now mass capital M is going to collide with the mass small m at position B. So theta, and this is position B. At this position, small m and capital M are going to collide with each other. This capital M is going to move up the inclined plane, let us suppose with the acceleration of a3, and mass small m is going to move down the inclined plane, and which we said that its velocity is v2 prime and acceleration is a2. And it is also given that this mass capital M is going to travel a distance of 0.5 meter. Let us suppose it stops at point C, and here is the mass M. Therefore, you can say that after collision, for mass capital M, initial velocity of capital M, let us suppose, is given as v3, and the final velocity of mass capital M is obviously v, which is equal to 0 because it comes at rest at point C. Final velocity of mass M at point C, and acceleration we said is given as a3. Acceleration is given as a3, which will obviously be retardation. So we can use the equation of kinematics to find out a3. So we can say, using equation of kinematics, v square minus u square is equal to 2as. Here s is our 0.5 meters, so final velocity is 0, so this comes as 0 minus V3 square is equal to 2 into A3 multiplied by 0.5, and A is equal to A3. So we can say our V3 square is equal to minus 2 into A3 into 0.5. We can find out value of A3. So let us, this is our mass capital M moving upward with the acceleration of A3, and we are going to have mg downward direction. This angle is theta, this will be theta. So we are going to have mg cos of theta, and this will be mg sine of theta, and we are going to have friction Fr once again in downward direction. And here we can find out our Fr. Fr will be equal to mu into normal, and n is equal to, sorry, this is capital M. So Fr will be equal to mu capital M g cos of theta. So we can write the equation as MA3 is equal to mg, sorry, capital M sine theta plus Fr. Substitute the value of Fr, we get MA3 mg sine theta plus mu mg cos of theta. M cancels out throughout, so we get A3 is equal to g is common sine theta plus mu cos theta. We substitute the value, we get A3 is equal to 10, sine theta is given as 0.05, mu is 0.525 rather, cos theta is 0.99. So once again we get A3 is equal to 2.99, and this will be also a retardation. Okay. This is retardation. Therefore, A3 will be equal to minus 2.99 meter per second square. So we already know the equation for V3. Substitute here A3. We get V3 square is equal to minus 2 into minus minus will be plus 2.99 into 0.5. So from here, this will be equal to 2.99, or we can say V3 will be approximately equal to 1.73 meter per second. So this is the velocity of mass capital M after the collision. This is the velocity of mass capital M after the collision. Now we got all the velocity values. We can use those to find out the coefficient of restitution, that is E. You can say coefficient of restitution is equal to relative speed after collision relative speed after collision divided by relative speed before collision. So after collision, both M and capital M are moving in opposite direction. So we have small m moving in downward direction and capital M is moving up the inclined plane. This is, you can say, after collision. So therefore, its velocity is v2 and its velocity we find out is given as v3. Therefore, coefficient of restitution, that is E, we can say our E is equal to v2 plus v3, and before collision capital M was at rest, only small m was moving, and we get this as v1. Substitute the value, we get 5, and it was v2 prime, sorry, this was v2 prime, and 5 plus v3, that is 1.73, and we found out that, you can say, v1 we found out is 8 minus 0. So we get E is equal to, this comes as 6.73 divided by 8. So we can say from here the coefficient of restitution E is equal to 0.84. This is the value of coefficient of restitution. This is the value of E. And finally, we are going to find out the mass of capital M. In this case, we can use conservation of momentum. So using conservation of momentum, by conservation of momentum, you can say before collision momentum is equal to after collision momentum. Before collision momentum is equal to after collision momentum. So before collision we have only small m moving with the velocity of v1. Capital M is having a velocity, it is rest, so this is 0, is equal to m v2 prime and plus m multiplied by v3. Therefore, and this v2 prime is in opposite direction, so we can put it here as a minus. So we get this as m v1 is equal to minus m v2 prime plus capital M v3. We substitute the value, mass m is given as 2, v1 we get as 8, is equal to minus 2 into 5 plus capital M, and v3 we found out as 1.73. So we get this as, this will be 16, this will be plus 10, is equal to 1.73 multiplied by m, or we can say our mass m is equal to 26 divided by 1.73, which we get approximately equal to as 15.12 kg. So So this is the mass of capital M. This is the mass of capital M. And in this case, for the conservation of momentum, there is no need to include the value of the friction because it will be acting on both the blocks simultaneously, so its value will be a constant value. So there is no need to include the coefficient of friction, and there is no as such external force acting on it. This completes the question. Thank you.